so we're looking at lesson 5.5, multiple angle and product to sum identities. And in this lesson today, we're going to focus on double angle identity. And next class period that we meet with the whole class, we will focus on half angle identities. You still need to use the other identities that you've learned, but these ones can help you to solve certain problems. Honestly, sometimes we don't need this. Remember how we had 2 theta in there? And a lot of us were solving and then dividing by 2? There's a quicker way to do it if you know double angle identities. And sometimes it's quicker, sometimes it's not. And if they tell us to do it, like where it says example 2, it says find using double angle identities, then we have to show that we know the double angle identities to do that. So let's take a look at what the double identities are. We're only going to look at them for sine, cosine, and tangent. And the good news is there are only 3, 1 for each one. You could change cosine to look a different way. I would suggest only memorizing one of them, though. So our first one, we have sine of 2 theta. So rather than solving and finding the angle and then saying, oh, that's what 2 theta is divided by 2, we can simply evaluate it in some cases by doing 2 sine theta times cosine theta. For cosine of 2 theta, we can do cosine squared theta minus sine squared theta. Now there's 2 other identities that are used for this. This is the one I use primarily. You could easily derive the other 2 if it would be more convenient to only use the value of sine or only use the value of cosine. I don't necessarily know when that would happen, but sometimes you may only have one available to you. And if that's the case, you can actually turn that into 2 other things. You could do this. Sorry? So here's the other thing. I could make sine squared 1 minus cosine squared. Distribute the negative, I'd have 2 cosine squared theta minus 1. I could also change cosine squared to sine squared. I'd have 1 minus sine squared minus sine squared. So I'd have 1 minus 2 sine squared theta. I don't recommend memorizing all 3. It's probably not going to be particularly helpful for you too. But if you memorize the first one, and you need the others, you could always derive them using the Pythagorean identity for sine and cosine. And then tangent squared, or not tangent squared, tangent of 2 theta is equivalent to 2 times tangent of theta divided by 1 minus tangent theta squared. So those are the 3, 1 for sine, 1 for cosine, 1 for tangent, double angle identities. In example 1, they say evaluate the expressions involving double angles. Find the exact values of sine 2 theta, cosine 2 theta, and tangent 2 theta. It's important to read the directions because if I were just looking at letter A, I'd give my answer and think I was done. Okay, what's the value of theta? Well, I can find that on the calculator. But that's not what they're asking us to do. They're asking for exact values, not, oh, figure it out in the calculator and use sine inverse. But find exact values in this quadrant between pi over 2 and pi, and then give me the values for sine 2 theta, cosine 2 theta, tangent 2 theta. So which quadrant are we in? If we're
2.
Between pi over 2 and pi, we're in quadrant 2. So since we're in quadrant 2 for this problem, I'll leave those in so that you can see them. That means our terminal ray is here. And here's the origin right there, that T. And so there's my terminal ray. It creates a right triangle. Here's theta, or at least a reference angle for it. That's for theta. And for sine is 3/4, so opposite hypotenuse, or y over r. You just have to find the value of x, which would be x squared plus 3 squared equals 4 squared. X squared plus 9 equals 16, so it's going to be 7, so it's going to be the square root of 7, except it's in a negative direction, so it's negative square root of 7. Because we're in quadrant 2. 2. The x-coordinate is negative, the y-coordinate is positive, the radius is always positive. So now they want us to find sine of 2 times whatever the heck this angle is. They don't really care what the angle is. They didn't say find theta. They don't want a decimal approximation, so you shouldn't use your calculator. You're going to use the double angle identity of sine 2 theta equals 2 sine theta cosine theta. Well, sine theta we already know. Sine theta is 3/4. So right now I have 2 times 3/4. By the way, that's 2 over 1. I have some people who are still multiplying denominators by numerators. Shouldn't be doing that with fractions. Cosine of theta would be adjacent over hypotenuse, negative square roots of 7 over 4. So when I multiply across the top, I get 6, negative 6 square roots of 7, which we're going to reduce in a second. Some of you already did, over 16. But 2 will go into both of those, making it negative 3 square roots of 7 over 8 when I divide a 2 out of both the numerator and the denominator. Any questions on that problem? For cosine of 2 theta, I'm supposed to do cosine squared minus sine squared. Well, I already know what sine of theta and cosine of theta are. Cosine is negative square roots of 7 over 4, so I have to square that. And then I have to subtract from it whatever 3/4 squared is. 3/4 squared is 9/16. Negative 7 squared, or negative square roots of 7, is 7. Because negative times negative is positive, and square root of 7 times square root of 7 is 7. And then 4 squared is 16. So this becomes negative 2/16, which reduces to negative 1/8. Any questions on that? All right, and I'm running out of room because of using the board, so I'll have to erase this in a second. We have to do tangent of 2 theta, which is equivalent to 2 times tangent theta over 1 minus tangent squared of theta. Well, 2 times tangent. Tangent, I'm not going to rationalize the denominator until the very end because some other stuff's going to happen to it. So tangent itself is 3 over square roots of negative 7. So I have 2 over 1 times 3 over negative square roots of 7. And that's all over 1 minus tangent squared. Well, if I square 3 over negative square roots of 7, I'm going to get 9 over 7. I'm going to make that 1 a 7/7. 7/7 minus 9/7 is negative 2/7. On top, when I multiply that, I have 6 over negative square roots of 7. Still not rationalizing the denominator yet because I'm going to simplify before I get there, and then I'll rationalize it at the very end. So now I'm just going to multiply by the reciprocal value of this, which is 7 over negative 2. That's going to give me 42 over positive 2 square roots of 7 in the denominator. 2 goes into 42 21 times. So I have 21 over the square roots of 7. I'm going to rationalize that denominator to get 21 square roots of 7 over 7. And 21 goes, or 7 goes into 21 3 times. So 3 square roots of 7 is the final answer for tangent of 2 theta. 3 square roots of 7. That one actually might have been easier to do a different way. But when not with this, not when we're evaluating 2 theta, we'd have to know what theta is first and the exact value. All right. Any questions on example 1? Example 2, find each using double angle identities. Yes, the traditional way of doing this is saying, oh, 540 is not on my unit circle, so what would I do? How would I get it to be on the unit circle? Add or subtract 360 until I get it to be between 0 and 360. And then I would just evaluate it there. That's not what they want us to do. I mean, that's the easier way. Obviously, if you were just said, hey, what's this value? That would be probably quicker. But sometimes this can be quicker too. It depends on the problem. If it's tangent 1, it may or may not be. So with this one, though, I can use double angle formula because I can say, well, this is really sine of 2 times 500 divided by 2 is 250, 40 divided by 2 is 20, so that's 270. 2 times 270. So what I have is 2 theta. I'm using the 2 theta rule. Well, for sine, that is 2 sine of 270 times cosine of 270. Sine of 270 is -1, so I have 2 by -1, and cosine of 270 is 0. So this is just 0. And I've shown my work for it that I did. Normally, it wouldn't be a big deal to not show your work because you're doing everything off the unit circle, but this is saying using the double angle identity. So I have to show how I made it look like a double angle identity and what it is I was evaluating to get the value of 0. On your BA, you will have part of it that is non-calculator and part of it that is calculator-based. So just be aware of that. You will have your unit circle available to you. All right, go ahead and take a second to try letter B.
What's like on the 2 times 270? What's on the bottom of that?
Right here?
No.
Up here?
No. Stuff there, right there.
That's 2 theta. I wrote 2 times theta. If you got square roots of 3, then you have the correct answer. So here's what you need to do. The tangent rule for tangent, first it says using double angle. So I'm going to multiply that by 1/2 or divide the numerator by 2. Gives me 5 pi over 3. That's what we see right here, 5 pi over 3. 2 times that is 10 pi over 3. The rule for tangent is 2 times theta, which in this case is 5 pi over 3. Guys, I'm not sure why you're talking, but I'm recording. I appreciate if you did right now. If you have a question, raise your hand. We'll go over it. So 5 pi over 3 is the angle we're evaluating for tangent. Tangent of 5 pi over 3, that's negative square roots of 3 over 2, divided by 1/2 or times 2 over 1. So it's just negative square roots of 3. So in the numerator, I really have 2 times negative square roots of 3. In the denominator, I have 1 minus negative square roots of 3 squared, which is just 3. So now I have, in my numerator, negative 2 square roots of 3 over, that's going to be negative 2. The negative 2, so the numerator and the denominator divides away, leaving just a square root of 3 for the answer. Questions on any of those steps? Yes, sir. No, because it is, hold on. Come on. So the whole point of using the trig identity is, before we had to prove trig identities, we still have a couple of those in this unit, but the whole reason we're doing this is solving equations that involve trigonometric functions. When you get to calculus and higher levels, if you take higher levels, you will encounter trigonometric functions, and you'll have problems that involve them. You have to know how to solve those equations to get to your answer. So solving on the interval from 0 to 2 pi, so I don't have to do the whole plus 2 pi n and all that, and then for tangent plus pi n. We're solving these. Now before, when we solved, you've solved problems like this before. Okay, but now we're actually practicing using the double angle identity. It will be much more efficient to use that if you know that identity. Because before you had to convert this to opposite of 1 minus cosine squared, or maybe you converted, well, you can't convert the other one, and then get it all to one side, and then factor. By knowing double angle formula, we'll cut out some of that factoring and some of those steps and make it a little simpler. So if I know, why isn't this working? Whatever. Since I know what cosine of 2a is equivalent to, it's equivalent to cosine squared of a minus sine squared of a, right? All I did was replace theta with a. And that's equal to negative sine squared of a. Well, when I go to solve this, I'm going to try to get my trig functions on one side, right? You're either going to add this or subtract or add it to the other side, right, to get everything equal to 0 if you want. Sorry?
Why is it minus sine squared of a?
Because that's what it was right here.
I know, but did you have to change it?
Oh, this is the formula for cosine of 2a.
Got it.
It's the double, not formula, identity, the double angle identity for cosine.
Oh, the signs just cancel out.
So the signs are going to go away, and I'm left with cosine squared a equals 0. I didn't have to use the Pythagorean identity to make them all cosine squareds and then worry about factoring stuff or getting everything, like, it just happened right here. So what I have here then is cosine. When is cosine squared? Well, if I take the square root, I've just got cosine of a equals plus or minus 0, which is 0. And when is cosine 0? At pi over 2 and 3 pi over 2. So there are my two answers for letter A. I'm not too worried about extraneous solutions because I didn't square the problem in order to solve it. Go ahead and take a second and try letter B. This is our last example for today. So if you got 0 and pi as your answers, then you can start working on today's assignment, which I'm going to write down. Then I'm going to go back and solve for anybody who needs to see. Page 352, 1 through 14. If you didn't get that answer, then pay attention as I go over the problem. 0 and pi. It's on the backboard also. And on your assignment guide. Over there. All right. So I changed the tangent of 2x using the double angle identity. That's really 2 tangent x over 1 minus tangent x squared. On this side, I have 2 tangent x over 1. Don't have to work on just one side because I'm solving. I can cross multiply. In cross multiplying, I have this times 1 and this times tangent squared. So it's, I better do a different color. 2 tangent x minus 2 tangent x cubed. That's from doing this with this, that cross product. And then the other side, we have tangent x times 1, or 2 tangent x, so it equals 2 tangent x. Well, if you subtract 2 tangent x to get your tangents to one side, then that goes away, and you have negative 2 tangent cubed x equals 0. I don't have addition or anything, so if I divide by negative 2, I still have 0. Tangent cubed x equals 0. When I take the cubed root, here I divided by negative 2, here I'm taking the cubed root, I get tangent of x equals 0. And tangent is 0 at 2 places, 0 and pi. In terms of radians, or 0 degrees and 180 degrees. All right, any questions on that last example? All right, please start working on